All right, welcome everyone. It's my pleasure to introduce Beatrice Brienza from University of Torino, who will speak to us today about strong HKT manifolds. So,
Thank you very much, Jeff. So today I will say something about strong HKT manifolds and this joint paper with Anna Finago, Grancherov, and Misha Verbitsky. Two of them are connected, so for a hard question, pass to them. So let's start by saying something about the mathematical background of strong HKT structures. So what can we say is that the strong HKT structures can be considered as let's say, are the analog of hyperkähler structures in geometry with torsion. So I assume that everybody knows that an hyperkähler manifold is nothing else than an hyperemission manifold, and I'm going to describe what this guy is later, for which the Levi-Civita connection of the metric G parallelize IJK, which is equivalent to ask that if I consider the Lonomy group of the Levi-Civita connection, then this is inside SPN. And so in particular, we're going to see that HKT structures will be hyperemission structure for which there exists a connection with torsion with the Lonomy inside the SPN. So in this sense, these are analog of this hyperkähler structure in the context of geometry with torsion. And once for all, for me, N will always be the quaternionic dimension of the manifold. So the real dimension will be 4n, and the compass one will be 2n. But we have to mention also the physics, the ground, and in particular, actually strong HKT structures first emerged in string theory. And I should mention the foundational paper, which are the paper of Juan Papadopoulos and which is the other one, Gibbons, Papadopoulos, and Stell. But there are many others, let's say. So to introduce the HKT structure, I have to define what is the bismuth connection. So just for 3 minutes, I will stay in the mission framework. So let us fix. This is an Hermitian manifold. So M is a smooth manifold of dimension 2n, J is a fixed complex structure on M, and G is a Riemannian metric which is compatible with J. So it's a theorem of Strominger and 2 years later by Bismuth that on the tangent bundle of my manifold there exists a unique Hermitian connection Well, I'll call this the Bismuth connection. Oh, sorry. But you can also call this the Strominger connection. So there is a unique emission connection, nabla B, with total skew torsion. So what I'm saying here is that by emission connection, I mean a connection that preserves the emission structure in the sense that, let me call this, okay, nabla B. I'm asking that nabla Bj is equal to nabla Bg is equal to 0. And let me say what this totally skewed torsion means. I can write down the expression of the Bismuth connection, and nabla B XYZ is just the Levi-Civita connection plus a piece, which I will write here like H XYZ. H is a tree form, and it has a really precise expression since H coincides up to a sign with the C operator of omega, and the C operator is just the differential conjugated by the complex structure J. And what I mean when I mean that I'm talking about a totally schizometric torsion connection. So, if I write down this guy, which is nothing else than my torsion, using this expression here and the fact that the Levi-Civita is torsion-free, it's just a computation that this guy is precisely H. So in this sense, the torsion is totally schizometric since this guy is actually a tree form. Okay? And of course, I will call H the Bismuth torsion. Since H encodes all the torsion informations. Okay. So we have our emission manifold. We can associate the Bismuth connection, and we can associate also its curvature. But here we are in the complex setting, so we may trace it using the complex structure J. So let us define this guy, rho xy. Let me call this just rho b, maybe. This is just 1/2 sum 2n of Rb, xy, gei, ei. So I'm tracing the curvature in the endomorphism components. This guy is a 2 form, and actually is a closer to form. So the rho b is equal to 0, and it represents a function class. So rho b represents C1 of M. I'm going to give the last definition in the emission case, and then we will move to the hyperemission one. So it's just a definition that an emission structure is said Calabi-Yau with torsion whenever rho b is equal to 0. And this condition is equivalent to ask that the restricted autonomy of the Bismuth connection is inside SUN, where N is the complex dimension of the manifold. So here I'm in this situation. Secondly, I say that my emission manifold is strong killer with torsion or pluriclosed whenever the Bismuth torsion is closed. So if dH is equal to 0, which is equivalent by the definition of H to ask that the DDC of omega, where omega is the fundamental form, sorry, I forgot to say this, is equal to 0, or if you like the complex point of view, this is just del del bar of omega equal to 0. And I can actually couple these two conditions, and I will say that my emission manifold is Bismuth emission Einstein if it is Calabi-Yau with torsion and SKT. Okay? Okay. Now we move from the emission to the hyperemission framework. And we're going to see that in the strong HKT case, actually, these Bismuth emission Einstein structures pop up. So let us now fix on the hyperemission manifold. So the dimension of the manifold will be 4n, and I have a triple of complex structures, high JK, which satisfy the unitary quaternary relation, meaning that, okay, of course, this satisfies this. Minus the identity, j squared is equal to minus the identity, and k squared is equal to minus the identity. This is just from the fact that they are complex structures. But furthermore, what I have is that ij is equal to minus ji is equal to k, and the same holds for all the cyclic permutation of the three of them, okay? And then I have a metric G, which is compatible with I, J, and K. So this is just an hyperhermitian manifold. Okay. Whenever I have an hyperhermitian manifold, I can always cook up a 204, which will always be called by capital omega in this talk. This is just a 204 with respect to the complex structure I. So let me write the I in the bottom. And I can cook up omega by writing omega j plus I omega k, where omega j and omega k are the Cayley structures of jg and kg. Sometimes in the literature you can find 1/2 of this, but it's not really important for us. Okay. So if I am in this setting, so the setting of an hyperhermitian manifold, if I want to work with connections, I have two good candidates, let's say. The first is the Levi-Civita connection. I always have this guy. But the Levi-Civita connection is torsion-free, you know? And it is metric. But in general, in the non-hyperkiller case, we don't have any compatibility between this guy and the hypercomplex structures. In fact, the Levi-Civita connection, if you remember, parallelizes IJK if and only if my structure is actually hyperkiller. Looking more the hypercomplex point of view, I can consider the Obata connection. So the Obata connection has been introduced by Obata in the 50s. Again, this is a torsion-free connection. And it looks at the hypercomplex point of view. So it is, let me write this like hypercomplex. And here I am meaning that nabla beta I is equal to nabla beta j is equal to nabla beta k. Okay. But in general, again, this has no compatibility with the metric. So I have these two points of view, which seems somehow not related to each other. I can look either to the metric point of view or the hypercomplex one. Of course, whenever I have an hyperhermitian structure, I can consider the associated Troy-Bismuth connections. So I have my, let me write this here, IG, JG, and KG. I can write down the Bismuth connection associated to each of them. So nabla BI, nabla BJ, and nabla BK, but in general, they differ to each other. So these are not really related with the hyperhermitian structure, but they are related to the fixed Hermitian structure, let's say. But now the HKT condition came to play. So definition, I have my hyperhermitian manifold, and I say that this is hyperkähler with torsion if the three bismuth connections agree. So nabla BI is equal to nabla BJ is equal to nabla BK, and I will write nabla B for the common bismuth connection. And of course, if we go back, not too much, but here, so the bismuth connection is Levi-Civita plus a piece corresponding to the torsion. But this is the same for the three of them because the metric is the same. So if I say that the bismuth connection agree, I'm just saying that they have the same bismuth torsion. And this is just H for me. Okay. So if I am in the HKT case, well, now I can consider a third connection, which is the bismuth one. And this keep the feature of both of them, since this is metric and hypercomplex. But it is not torsion-free, so this is as torsion. And the three of them coincide if and only if the structure is hyperkähler. So in the non-hyperkähler case, these are really, really different from each other. But there are some relations, so you can recover the bismuth connection from the Obata, and the formula is of Ivanov and Petkov. So you can play with three of them, let's say. So let me give the following equivalent definition. Let's say this is a theorem of Grantcherov and Poon, that actually the HKT condition is equivalent to ask that if we consider the 204, this capital omega, this is the Lie closed. So if we are in quaternionic dimension 1, and if we have an hypercomplex manifold, so if we are in dimension 4, so we can always cook up an hyperemission metric, so there always exists a G compatible with high JK. However, and also what I wanted to say is that if I cook up this 204, since I am in real dimension 4 or complex dimension 2, this guy is always still closed. So this is always HKT. So there was a question for here, if whenever I have an hypercomplex structure, if I can find a compatible HKT metric, but actually this is not the case. In fact, if n is greater than 1, we have plenty of examples. So plenty of hypercomplex structures with no compatible HKT metric. The first example was exhibited by Fino and Grantcherov. I don't remember exactly the year, but it was in quaternion dimension 2, so for n equal to 2 on Néel manifolds. There is a last thing that I want to say is really the link, at least in my opinion, between hyperkähler and HKT geometry, which is the existence of a local potential. So this is a theorem. This was proven by Magnussen-Swan. But I should mention also Grantcherov and Poon, I guess. And the theorem is the following one. So any HKT metric admits locally an HKT potential. And what is HKT potential? It's just a locally defined function that may call this function mu, such that basically I can recover all the data of my HKT structure from this local potential mu. So, for instance, I can recover omega I, omega j, and omega k. I recover this is equivalent to recover the capital omega or the metric G. And these are just 1/2 ddci plus dcj dck mu. Omega j is 1 over 2 ddcj plus dck cs dci mu. And omega k is 1 over 2 ddck plus dci dcj mu. Okay. I can also write down the expression for the metric and the capital omega, but it's a bit boring. There is a remark which is kind of important, and this remark is due to Grant-Sedov-Poon, that this function mu in the compact case is really locally defined. So if M is compact, then mu is never globally defined. Okay. So this is the background about HKT structures. So I think that now we are ready to define what a strong HKT structure is. We have all the ingredients to do it. So let me define. So let us pick. This is an HKT structure. I say that this is strong HKT. Whenever the common bismuth torsion is closed. Actually, as far as I remember, this was the original definition of HKT, but later it was dropped, this condition, because of really the lack of examples. In fact, we're going to see that this is really a strong condition on the manifolds. Okay. And probably a very easy example is given by hyperkähler manifolds. And why this is true? Well, of course, in the hyperkähler case, as I told you, the common bismuth connection coincides with the Levi-Civita one. So nabla B is the Levi-Civita. And furthermore, the torsion is 0. And so also its differential is equal to 0. So H is identically 0 and also is differential. Okay. But the most important thing for us is the link between these structures and the bismuth emission Einstein one. So in fact, let us pick our strong HKT manifold. So if we use, so this is strong HKT. So if we use the HKT condition, and if we consider actually the common bismuth torsion, we have that this guy has a lot of symmetries, because this preserve I, this preserve J, K, and the mercury G. Sorry, this is 0. And so by the Holonomy principle, so this is Holonomy principle, what we have is that its holonomy is contained inside SPN, where N is this N here. Okay? But SPN is a subgroup of SU2N, which is the complex dimension of the manifold. And so from this first condition, what I get is that IG, JG, and KG are Calabi-Yau torsion. If you remember, a Calabi-Yau torsion condition, it was simply restricted holonomy of the bismuth connection inside the SUN, or equivalently, the vanishing of the bismuth heretofore. But from here, we immediately get that each of them is Calabi-Yau torsion. On the other hand, if we consider the strong condition, then we have that the common bismuth torsion is closed. So DH is equal to 0, which in turn implies that HI Hj and Hk are closed since they are all equal to each other. And so each emission structure here R is KT. So if I put these two together, what I get that if I have a strong HKT manifold, each Hermitian structure individually is actually Bismuth-Hermitian Einstein. So I can use the theory of mostly compact Bismuth-Hermitian Einstein manifold in this hypercompact hyperemission setting. So the first phenomenon I would like to describe is what I would like to call the reduction of the holonomy, which basically came from the Bismuth-Hermitian Einstein case. So now the hypotheses are, so our manifold is a strong HKT, but I assume that my manifold is compact. Okay. I have that each emission structure is Bismuth-Hermitian Einstein, so Lg is BHA. And so I can use the result of Garcia Fernandez, Jordan Streets, Papadopoulos, I should mention also Apostolov, Barbaroli, and Streets. And I have the existence of a vector field V, let's call this VL, because I'm fixing the emission structure here, which is defined as 1 over 2, the dual of the Lie form minus the gradient of a normalized function f, such that this is Bismuth parallel, and well, Bismuth parallel implies also killing, so VL is killing. But furthermore, what I have is that VL is 0 if and only if the structure is scalar. So let me state this lemma. And this is the first lemma of the paper that I want to show you. So Bryancev and Verbitsky, that I have 3 of them a priori because I have 3 emission structures, but it turns out that all of them coincide. So let me call just V, just the common vector V. So how can you prove that these are equal to each other? Well, there are 2 ways, probably well, not most easy, but for me at least, it's easier in this way. So we want to show that 3 of them are equal to each other. So if you remember, VL is just the dual of the Lie form minus the gradient of the function. But we are lucky. In fact, these 3 guys, so theta I, theta j, and theta k, agree to each other. So we can define theta to be the common Lie form. Sorry, I should have mentioned this. Probably said this. This is the Lie form. So theta I is equal to theta j is equal to theta k. And this was known for the HKT case by Ivanov and Petkov, but recently it was shown by Fusi and Gentili that these also hold for hyperemission metrics. So hyperemission, this is Fusi and Gentili. So now basically what I have to show is that these 3 gradients are the same, but I can use, for instance, that my vector is killing. In fact, my vector killing says that I have that the Lie derivative of G with respect to VL is equal to 0. So this is just 0. So I can trace actually this condition. And this is completely equivalent to ask that the Laplacian of FL is equal to minus the codifferential of the Lie form. But as you may see on the right-hand side, I don't have terms depending on the emission factor. This is the same for the 3 of them. So at the end of the day, what I have is that, the Laplacian of Fi is equal to the Laplacian of Fj is equal to the Laplacian of Fk. And here, I can use again the time is compact to prove that actually they must differ to each other by a constant. So they differ by a constant. And so as you may see, the expression of the three vector fields is the same. And of course, I have that V is equal to 0 by rephrasing this if and only if my structure is hyperkähler. So if and only if EJKG is hyperkähler. So if I am in a non-hyperkähler case, so non-hyperkähler, I have that my V is always different from 0. And also, I can use now that this is parallel. And since this is parallel and the Bismuth connection is hypercomplex, also I of it, J of it, and K of it are parallel. So basically, I have a reduction of Delaunay from SPN to SPN minus 1. And this is just because nabla BV, nabla BIV, nabla BJV, and nabla BKV are equal to 0. So I'm preserving a quaternion somehow. And by rephrasing this, I'm just saying that if I have a compact strong HKT manifold with holonomy of the Bismuth connection, which is exactly SPN, then it must be hyperkähler. And we use also this result to prove actually the existence of this vector field V to prove some result in the locally homogeneous setting. So in the locally homogeneous setting, the existence of HKT structure has been investigated a lot in the last, I think, 2 decades. And in particular, also the existence of strong HKT structures, but the results that were proven were negative results. In particular, if you combine the paper of Dottienfino and Berberis-Dotti-Verbitsky, you have that a Néel manifold has an invariant strong HKT structure if and only if it is a torus. So if and only if it is hyperkähler. And a similar result also for the almost abelian case by Andrade and Barberis. And here we were able to prove this result in full generality. So it's a, call this maybe. The Tassul manifold has an invariant strong HKT structure if and only if it is hyperkähler. And this was proven, just to give you ideas, by showing that the existence of this vector, which is non-zero, implies that somehow you have to do a little bit of effort, that the scalar curvature of my Soul manifold has to be non-negative. But then you can combine this with the result of Milden and Jensen about the sign of the scalar curvature of the left invariant metric console manifold. And at the end, you get that the norm of the torsion has to be 0, which in turn implies that nabla B coincide with nabla Levi-Civita, and so hyperkähler. That more or less the idea, but I don't want to go into details. What I want to mention is instead the problem about the lack of examples. So at least in the compact case, so I'm working the compact case, we have that any compact example has parallel Bismuth torsion. So yeah, I'm stressing out compact. So this was also a problem for Bismuth emission Einstein metric, but very recently compact examples without parallel torsion were found by Apostolov, Lee, and Ledili. but the examples are in dimension 6 and they are of course not hypercomplex. So the problem of finding example without Pala-Bismuth torsion remains in the strong HKT case. However, we have some hope. In fact, there is one possible candidate. So there is one possible candidate with non-Pala-Bismuth torsion. And this example has been constructed by Witten. However, it is not clear if it is as parallel torsion or not. So I think that the people are working on this. So since at least except for this example, which is a bit of mystery, any known example of compact string HKT manifold as parallel torsion, a reasonable thing is, okay, can we try to classify them somehow? And actually we were able to do this basing this result on previous results on compact bismuth emission Einstein manifold with Pala-Bismuth torsion. And we were able to prove this theorem. I should mention that the previous results were a result of Zhao and Zheng, myself, Annafina Gograncharov, and Barbara Filiponetta. So the result is the following one. So let us consider to be a compact, strong HKT manifold with Pala-Bismuth torsion. Well, then, how to find it cover of our manifold split has a product of two guides. The first is a compact, simply connected hyperkiller manifold. And the other one, this is a bit imprecise, but let me call this a Joyce hypercomplex manifold. So I'm not being precise here, but just keep in mind that Joyce hypercomplex manifold are nothing else than compact Lie groups with left invariant hypercomplex structures and B invariant metric. But here, again, I'm not really precise. But this is more or less what happens. What I want to say is something about the dimension 8. Because, okay, if we look at the case of Quaternion dimension 1, we have seen that, okay, or we are in the hyperkiller case, but if we are in the non-hyperkiller case, we have 4 vector fields which are Bismuth parallel, which are V, IV, JV, and KB. Well, if we write down the torsion, this is just a constant times IV flat, JV flat, and KB flat. And of course, this is parallel. And so by the result, then we have that this is either, well, hyperkiller, we set aside this. So in dimension 4, we have 2 Joyce hypercomplex manifold. So hyperkiller or tri or the observed phase. And these are the Joyce. So what about dimension 8? Well, dimension 8 is a little bit more complicated compared to quaternion dimension 1. I want to present some results in this direction, but before presenting them, I have to spend really, I hope, not more than 5 minutes about what is the Ricci foliation of an hypercomplex manifold. So now, but let me just still 5 minutes to talk about the Ricci foliation. Okay. So let us consider now we are not in dimension 8. We are considering just any hyperdimensional manifold. And we can consider the usual capital omega, which is the 204. If we consider omega to the power of n, then this is what is called a Curial form. What does it mean? It means that if I do j of the conjugate of it, this is always equal to itself, let's say. So this is what Curial actually means. But okay, apart from this, what we did is to define KR to be the line bundle, so the real, line bundle over M, of course, generated by omega n. And this is just an easy remark that, for instance, if I consider the canonical bundle with respect to the complex factor I, this is just the complexification of KR. Okay. So this is a line bundle, and we can define the so-called Obata-Ricci curvature. It's not the Ricci of the Obata connection, but okay, we're going to see in a moment what it is. So the Obata-Ricci curvature, I will call this capital theta. I hope that this is a theta. Is the curvature of the Obata connection on my bundle KR. Okay? My theta is actually a two form, and I can prove two facts. The first is that this is sp2 invariant. And by sp2 invariant, I mean that this is ijk invariant, so 1 with respect to ijk. And furthermore, this is exact. And this is kind of important because since this is a two form which is exact, the kernel of theta, I'm saying this always, okay, is involutive. So if I take x and y belonging to this kernel, then also the bracket belongs to the kernel. And this allows us to define, so this is definition, we gave the definition, I think, the first time, that the Ricci foliation is the subsheaf, of course it has no constant rank, curve of theta. Okay. Now, we are interested in strong HKT manifolds in dimension 8. So you're going to ask me, okay, why you're introducing all of this? Well,
Sorry, Beatrice, can I ask a question?
sure.
Uh, is this data like explicitly exact? Is there an explicit formula for of it as T of something?
No, we proved that it was not this, I mean, we proved that it was exact by using that the C1 is equal to 0, and it was a representative of the C1. But no, actually, I think that you can get the explicit expression, I guess. Yes, you can actually.
Okay.
If I remember well, yes. But I don't remember exactly what it is. Sorry.
No, okay, no problem. Thank you.
No, but in the case of our interest, it is is it actually clear what it is? In fact, in our favorite case, which is the strong HKT1, oh, sorry. Well, this theta coincide with the differential of the Lie form. Okay? So this is actually from the HKT condition, and from the strong HKT1, one can prove that the four vector fields V, IV, JV, and KV belongs to this subsheaf. So they belong to the kernel of theta. Okay, so this is how to relate this Ricci foliation with the case we are interested in. And actually, we use the Ricci foliation to prove that the distribution spanned by these four vector fields was actually involutive. So, okay, I don't have much time, but let me state the theorem and let's see what I can show to you. So let's now fix the eight-dimensional case. This is true in general, okay? This is a compact, strong HKT, no, simply connected also. Strong HKT manifold. Careful that I'm really fixing dimension 8. And for simplicity, I'm excluding the hyperkiller case. Then, well, I can prove three things. The first is that if I consider the foliation spanned by the four vector fields V, IV, JV, and KV, this is involutive. So it's involutive and isomorphic to U1 or plus SU2. Secondly, if you remember, my vector field V was defined in terms of the dual of the Lie form minus the gradient of a function f, and one can actually prove that f is constant. And third, one has a property on the hyperemission structure, which makes it, let's say, rotational. In fact, LIV omega j is equal to omega k, and the same holds for any permutation of ijk. Okay? So the proof that this is isomorphic to U1 plus SU2, and these two are really heavy computations. How we prove this? We use a lot that the full, in our case, our tangent bundle is F plus an orthogonal. We use the distance dimension 4, so we have a lot of geometry in dimension 4, but we really had to combine the three connections that I described to you. So Levi-Civita, Bismuth, and Deobata, and we also use Deobata actually. But I can show you that this is involutive, and is where the hypothesis on compactness and simply connectors came into play. There is a paper of Jeff and Aaron, which was out after our paper, and they deal with the situation in full generality. But, well, I want to mention this. So I will just present the proof of this involution of the distribution, which is kind of nice. So, but it's only an idea of proof. And we use the Ricci foliation that I introduced to you. Idea of proof of one. So the idea is the following one. So we have our F, which is the span of V, IV, JV, and KV. And we have seen by the strong HKT condition that this is inside the kernel of my capital theta, which again, in our case, is just the differential of the Lie form. So let me split my tangent bundle in this way. And by contradiction, we assume that there exists W1 and W2 in F, whose bracket is not in F. So W1, W2 is equal to a W3 plus an X. This is inside F, this is inside F orthogonal. And since I'm asking that this is really not in F, X is different from 0, that's the point. Then if X is different from 0, we can pick a point in my manifold for which XP is non-zero, and then of course I can find a neighborhood on which X is non-zero. But now I can write X as, by this expression here, the bracket of W1 and W2 minus W3. But this belongs to the kernel of capital theta. And this is true because if you remember, my Ricci foliation is involutive. And this belongs again to the kernel of theta, since F holds this property. And so this is in the kernel of theta. But X is linearly independent with V, IV, JV, and KV. And here, I may use these general properties that theta is SU2 invariant. So if X is in its kernel, also IX, JX, and KX should be. So I have that at least on UP, P, IV, JV, KV, and X, IX, JX, and KX are in the kernel of theta, and actually they span the whole tangent bundle. So this is in the kernel of theta, and since I am dimension 8, of course, theta is equal to 0, which is precisely the differential of the Lie form. This holds on a neighborhood. And now we can use this proposition, which is kind of intriguing, where we prove that if we have a compact, simply connected, strong HKT structure, if the theta is equal to 0 on a neighborhood, so let's call this UP since for us will be this one, then my manifold is hyperkähler. And so since I am not in the hyperkähler case, I just proved that my distribution is involutive. This is the idea of the first point. Again, all the other proofs are really, a lot of computations are not very nice to be described, let's say. But at some point, if you remember, I told you about the description of an HKT structure in terms of the HKT potential. And actually, you can describe also in the eight-dimensional case the geometry of these manifolds in terms of the local potential. In particular, you can describe the vector fields B, IV, JB, KV. And
Sorry,
I want...
Beatrice, can I ask something?
Sure.
So the last proposition, is this not just the fact that you have pretty close plus conformally balanced, then you have a Kähler?
But this is not really conformally balanced. It is conformally balanced on a neighborhood.
Okay.
Yeah, is the point.
Okay.
Because if it is 0 locally, then you prove that this is 0 globally, and then you can use that result. Yes. Is okay?
Okay, thanks.
Thank you.
But is this neighborhood is dense, or what is this? Is a neighborhood of what?
Just an open neighborhood. Yes.
But also, is the argument local in nature? Because I would imagine by some kind of unique continuation, you could claim
We proved using, again, the potential that you have a real analytic structure, and this guy is real analytic. So if the theta is equal to 0 locally, then it has to be 0 globally.
Okay, that's what okay. Yeah.
Okay, that's it. Okay, good. And let me mention only this proposition that I was telling you, link the local theory of the HKT potential with the geometry of this vector field that I described to you. So this is proposition. So in terms of the local geometry, for instance, my vector field dual form, can be written in terms of two functions. This is JdP plus d mu. This is my HKT potential, while P is a function that in turn depends on mu. But what more importantly is that in function satisfy del bar I J del of P equal to 0. Okay, now I don't have really enough time, but I want to mention only the last result of the paper. So let me go back to the splitting theorem. So as I told you, we don't have, at least except for the Witten example without parallel torsion. In fact, all the non-example can be recovered from this. If I am in dimension 8, the only example that I have under the assumption of compact and simply connected assumption. So far, we have only hyperkähler in dimension 8 or this Joyce manifold. But if I require compact and simply connected, this is just SU3. Okay? Now, SU3 has a nice description. A non vibration over CP2. Unfortunately, we were not able to prove that SU3 is the only example, at least in the compact simply connected case. But we can prove a structure theorem anyway. And you're going to see that the structure is not too different from this one. So the last theorem for today. So any simple connected strong HKT manifold KG is either hyperkähler or has the structure of an off vibration over a four-dimensional Riemannian oriented orbifold. And by the long exact sequence, you can also prove that the first orbifold fundamental group is equal to 0. So in dimension 8, apparently, we have either hyperkähler or they have this structure of an off vibration over a 4D orbifold. And as you may see, the case of SU3 perfectly fits in this. And I conclude here. Thank you very much.
Thanks. Thanks so much. Are there any more questions? Wow, Zoom has improved a lot. I haven't seen all this. That's funny. I guess this proof is very eight-dimensional somehow.
Yeah.
I mean,
Unfortunately, yes.
but should this Ricci foliation play a role in general, you think? I mean, is there...
Well, the point is that for us, it played really a role because we weren't able to prove the involutive thing. And we weren't able to prove that this guy was involutive. And actually for us, the Ricci foliation was really helping because using it, we were able to prove that this was involutive. But I don't know if in general it has some role. For sure it has it in dimension 8, but in higher dimension, I'm not completely sure.
Right. Well, I would guess another point here is you have to, even once you know it's involutive, I guess then the Lie algebra is either what you say or
Yes.
like T4, but you have to
Yeah.
somehow rule out that it's trivial, I guess, right?
Yes, you have to rule out that it's a form, but I think maybe Geo knows this better than me, that R4 leads immediately to hyperkähler. I think so. But not completely sure.
Well,
Maybe.
In general, it's not clearly immediately, but that's what one expects, yes.
Mm.
The trouble is the number 3 here is the place, this property 3 is exactly the place where you need dimension 8 most heavily.
But also this one.
Yeah,
Oh.
this is where you cannot avoid it.
Yeah.
Well, and maybe that fact can be proved independently. This like if IV, JV, and KV all commute, then somehow it should be hyperkähler.
Yes,
Even like
should be a way. We haven't think
Yeah,
about it.
but this is, yeah, it's possible and it's reasonable to expect that.
Yeah.
oh, okay, yeah, I see. Any others? Okay, well, if not, let's thank Beatrice again, and yeah, and I'll stop the recording.
Okay, thank you.
Thanks.